So there you go.
Okay.
All right, go ahead.
Yeah. Okay. So real quick, just brings people up to speed as we have population kind of scroll in. Expect the full attendance probably in the next 3 minutes. But we've been in existence for about a month and a half. And there's a Greg Stover. I'm gonna. So
an interim guest based on timing.
So we've kind of evolved to a point where last week we talked briefly about what makes a mission critical pipe solution, looking from the perspective, and the ACF, Advanced Cooling Facilities team, is focusing on the connection from the advanced cooling solutions like the IT cooled rack out to the data center, the facility water solution and chill water solution. We started talking last week about what defines a mission critical pipe. We're going to go back that discussion next week. We're alternating every 2 weeks. And today's discussion, we're kicking off the concept of reference designs. Is there a benefit to reference designs, or what would the reference design concept do for our community? And is it something that OCP should be sponsoring? And as mentioned earlier, due to popular acclaim for me not to speak so much, we have John Minash, who is the co-lead of the program, is going to be covering most of the topics today. It'll probably be hard to keep me from talking every now and then, but I'm even just to try to keep from distracting people, I'm turning off my camera here, and you got John speaking. So John, you take it from here.
Yeah, hi everyone. Please, this is my first time, so I'll do the best I can here. So on the topics of reference designs, Don and I have been talking quite a bit with people in the background here, and we've been trying to understand what would make sense to be a reference design for the type of people who would be effectively the users of the OCP recommendations. And one of the items that keeps coming up is the idea of a CDU, or a heat exchanger of some type, be that purpose-built or a purchased CDU, and how we connect into the building with that. And I mean, that's largely the intent of this entire subcommittee. So what I am proposing, and what I'd like to get some feedback on and discuss today, are things that would go into a reference design. Among these are the formats that we would provide. Don and I have talked about doing papers, and also kind of a PowerPoint type of outputs, things that we can put on the wiki, but also maybe producing some CAD or BIM files that might be helpful, if nothing else, for graphical understanding of what's going on. And I'm going to share my screen here shortly and show you some things that kind of relate to that. I'm sure everybody on this call is familiar with this kind of an installation. Now, I don't want this to be an ad for anybody. I do have a little bit of Vertiv gear. I'm a Vertiv employee. I have some Vertiv gear in here, but this could be any one of your pieces of equipment on here. I just want to bring up some ideas and get the discussions rolling, and not only talk about the design, but also talk about what we want to present for reference designs. And a couple of items that come to mind here, and I'm going to now share my screen so we can talk about this kind of live. Share, okay. Oops. So this is a kind of a snippet of a design at the concept level. Nothing in here is really worked out too much, but this might give us an example of how we might implement liquid cooling in a existing data center, an existing co-location space, where there is, for example, along the periphery of the room, on the wall, or into the floor. And by the way, that's another topic we really love to have people chime in on. My thought is we're going to hit both, and a lot of newer data center of different types, be they hyperscale or co-location or enterprise, are encountering slab floor or designing for slab floor. So I think we need to at least address it. We're not always going to have the benefit of being able to use a raised floor environment. But so if you take a situation where you have chilled water header running along the outside of the room, the question becomes, how do you tie in your new liquid cooling system to that? So this is just one take on it, but it's a pretty common one, I think, as far as how the people on this this call will interact. So I'm going to say, please feel free to interrupt me when I'm speaking here, because there's a lot here. And again, it's not a commercial for Revit, not a commercial for Vertiv. These are just concepts, and I'd love to have everybody's feedback. So,
hey, John, this is Vali. Just a quick comment. You slipped into the old trap of calling it chilled water, and I think we got to be careful because
yeah, fair point. Okay, so not chilled water. What are we're going to call
cooling
it?
water. Just call it cooling water. It can be at a range of temperature depending on whatever W class conditions we want to talk about, but that's a variable. It's not a fixed.
Certainly. Okay. Very fair point. On that point, though, it's worth noting that if we consider some of the users here are going to be IT managers, IT owners of these buildings, not necessarily mechanical or electrical engineers, there are considerations that somebody with experience is going to know. One that I always try to bring up to people when they're laying things out is insulation, right? If this is, cooling water, fine. If it's cooling water that's below the dew point, we're going to have condensation. So most loops that you're going to see that are chilled water, in the traditional sense of chilled water, are going to be below, on the supply end, going to be below dew point and condense. So they're going to be insulated. So the reason I point this out is that end users might not be so aware of this. So this is a CDU example here. This is the secondary loop. This is the primary loop. Now these are, I believe, 2.5-inch connections, and these are 3-inch connections on the cooling or chilled water side. But they look a lot bigger. It's because they're insulated, right? So you'll have users that are thinking they have enough space, but when they actually insulate and throw something under the floor, especially under the floor, they can run out of space pretty easily. So one of the points there is we need to give users a knowledge of how to tie into these. Another one is this. I've drawn this as an 8-inch pipe, just for example. So an 8-inch header running around an outside wall with valves that are valved and capped for future use. Well, how do you tie into those if this is a 5-inch, but you want to go to a 3-inch, right? So the users have to know what that will mean and how they'll do that. These CDUs, I drew these based on a design I've used that has internal valving over here. Otherwise, I'd want to have valving on here to be able to remove this for maintenance, for working on it. So it's likely that they're going to, if they encounter stub offs on an existing loop of chilled or cooling water, that they're going to be larger or smaller than they need, and they need to know what that means. So that's one of the topics. How do we come off of central existing loops of cooling water? Like Vali mentioned, could be chilled water, could be a condenser loop, could be something else. But as long as it's appropriate. Then how do you deal with redundancy? Here's another one. This is a bad design, by the way. I cut this out from something else. There were other units over here, but having a supply and a return, this is not designed as a reverse return or Tickleman loop at present. So this would have a lot less pressure over here than you'd have on the units up here. So I would say that the recommendations as far as pressure equalization probably should be in there. If we go to individual outlets for devices, and by the way, what I've drawn here is, and if Ralph is on here, I really apologize, Ralph, but here this is an immersion cooler with all its detail. If we were to put this in here, what kind of a supply and return are we going to want? Do we want just shutoff valves? Is that dependent on what the gear is downstream? or do you want to put a triple duty valve over here? And are they, I know they're called other things in different parts of the world, multi-purpose valve, for example. Do we want to use pressure dependent valves or pressure independent valves? And then when we tie in, what kind of flow rates? So the idea here is we could produce a graphic like this. You know, we can start from scratch and put in a bunch of examples, above floor, below floor, both for the cooling loop, a secondary cooling loop, CDUs, direct from the source if we're going right to chilled water to the location, and then running up above. So I'd like to get any feedback on whether or not maybe producing at the very least graphics, but maybe reference designs that we provide in either Revit, which is proprietary. We could also provide IFC, which I wanted to show. IFC, for those who aren't aware, it's a little buggy, but it's an open standard for BIM interoperability. So it's basically open standard BIM modeling. I think if we were to produce something as OCP, we should strive to put it out. Maybe we'll put it out in Revit, and somebody could maybe convert to ArchiCAD or some of the other programs, but we could also put it out in IFC, so we have a truly open solution. So I just wanted to
John, sorry
mention
to
that.
interrupting you.
Please.
Peter from Germany. I
Yes.
think we have talked in one of the last meetings that we don't talk about the CDU side. So we're only talking about the connection from the facility to the CDU, because of the CDU is part of the company building the immersion cooling or the rack-based cooling system.
Yep. Okay. So you're saying, Stephen, that we should be focusing really here then, right? If
Yes.
if it's
Yeah,
going
but
to a CDU.
I thought that we acknowledged, though, that sometimes a CDU may be agnostic, right, to what's coupled into it, and what you're showing here, where it could have some immersion and maybe some cold plates within the racks itself. So I thought we decided there could be two scenarios where we would have some purview over the other side of the CDUs, like you're showing here, John.
Yeah, and I understood it like that as well, John. And I'll go so far as to say, right here, these are, I would say, small package, probably 200 to 300 kW type devices, but based on the pipes that I've got on there. But you know, this could also be a centralized plate and frame system installed. So I think I agree with John there in that this stuff needs to be addressed as well. I would say when we get
because
down to this
I'm
level,
aware of it. I'm aware of at least a handful, half a dozen or so CDU manufacturers that have nothing to do with the IT side of the equation. So this definitely exists, right?
Yeah. So
Right.
yeah.
So
Jason,
that's my recollection as well. But I think one of the things that we need to be very careful of is, as a group, we need to be highlighting what the issues are that need to be addressed. I think we need to be careful about being too prescriptive about how to do that. Specifically, John Minash, you mentioned, you know, do you do pressure independent, pressure dependent? Do you do triple duty valves, et cetera, et cetera? To a large degree, I think, you know, we need to bring up, you know, the issue of hydronic balancing. We need to bring up the issue of being able to shut off and isolate individual pieces of equipment, whether that be a CDU, whether that be a rack downstream of a CDU and a vendor agnostic solution, et cetera. But to get to the point where we're telling them that you need to do this by putting in a triple duty valve, I think we're going too far.
Yeah, no,
Yeah, but to your point though, if we should give guidance though, that if the IT equipment itself, right, that's using this side of the CDU doesn't have flow regulation, right, then we may want to give them guidance, not with any specificity of the type of valve, but say, hey, you need some provision to set the flow through this device if it's just some cold plates that don't have flow regulators, right? So we might want to give some guidance, not necessarily specify the top type or automation, but say you better have the ability to set the flow to things that don't have the ability to control the flow of this coolant loop itself, right?
Agreed 100%. And that's what I'm saying is that in my opinion, OCP's guidance needs to be these are the issues that you need to make sure are addressed, whether they're addressed with your facilities design, whether they're addressed with the ACS solution that's being provided, but these are the considerations that you need to account for. And at some point, and I think that's the point, we hand it off to the owner and the owner's design team and say, you figure out how to go do this, but these are the things you need to make sure you've covered.
I'm going to just append to that, John. I agree, but there are the statement about how you go about doing that is up to you. I think we need to at least offer some guidance as to what's available. Maybe it doesn't have to be. Well, that's my stance. I don't know if if anybody wants to chime in on it, but saying that pressure independent valves are available, saying that types of different devices are available, not necessarily naming one or saying a particular type has to be used, but I was thinking the audience that is going to consume this might want to know that, might not know that. Is that a bad assumption based on who we believe is going to consume this data?
I think, in my opinion, I think that's a fair assumption. I think it's, there's a lot of stuff that's changing in the industry that supports what we're doing as well, that may not necessarily be focused on, the IT side of things, just general industry stuff. So I think making sure that people know what's available is good, but but specifically telling them how to do it, I think is going too far.
Okay. So John, what are your thoughts on the idea? I'm sorry, John.
No, I was just supporting that 100%, to offer examples, but don't be prescriptive. Yep.
Mm-hmm. So, okay, so let me back up a step and say, do people feel that providing these kind of graphics for let's say a handful of kind of known implementation schemes, is that helpful or is that too prescriptive?
From an engineering side, I think we don't need a 3D construction. We need a schematic draw to be working with it. For the general public, a 3D view is fine. But from the engineering side, I would prefer the schematic view of the component.
Okay. That's interesting.
Real quick comments here. I love where this is going. At the very high level, we're trying to speak to several groups. We're not trying to compete with the MEPs and the engineers who are still going to need to do the technical review. But a lot of owners don't understand, or what I'm hearing is that there's many situations where people are building data centers and the considerations of all the space, the pipe, and what might need to go in the future is not always considered. And anyone who's ever worked in an operating data center or seen operating data centers knows that over time, the empty space gets shut out. Okay, so at the highest level, we're trying to communicate in a visual way to people, both owners and engineers, that something like this is going to have to somehow fit in your data center if you want to add liquid in the future. It's going to be a living project. We're going to start out with a high level, pictures like this, and then we may actually have areas of specific recommendations where we boil down what kind of valves, pros and cons of different valves. But at the highest level, there's a need in the industry right now just to make sure you leave enough space for CDUs, pipe, and you think about whether or not the pipe's going to run above your rack or underneath the floor. And if you have a slab floor, someone needs to think if you're going to be liquid cooled ready, you need to have a pipe path. So anyway, I'll hand it back to you. Sorry, John, I couldn't make it through the whole call without saying something, but you're doing great. I want to give you a chance to catch your breath and go forward on this. So go ahead.
No, this is all good feedback. What I'm trying to kind of refine this down to is what that means. And John made some good, both Johns made some good points here. Again, I keep going back to who consumes this, and at least one of the use cases I see is a data center owner, somebody that sells space inside of a co-location facility, the people that are doing the business end of this data center, saying, I need to implement this. Here's what I have. I want to give that to somebody, right? I want to hand that off to somebody and have them help me implement it. Now that could be their internal facility engineers and or their hired MEP engineers and or both. But the people that are doing that handoff don't have the language, don't have the vernacular to get through that. So things like graphics like this make it a lot easier for people to digest. This was kind of where I was going with this.
How about we rephrase that as a question real quick? And I don't know, Jason, if you're still on the call, or Alex, how do you sell? I mean, what we're talking about here, how do you sell the potential for liquid cooling in your future data centers?
Yeah, hi, Don. Jason with Stack Infrastructure. Hi, John. Yeah, when we're selling liquid solutions to our customers, we're looking how to retrofit our existing design, how we can pull out a cray and use the tap-offs for the crays to feed a CDU, or go in some instances with elevated temperatures directly to the rack, bypassing the CDU off of that tap-off. But then we also provision future positions on our branch loops, so our headers, so that we can provide future positions to CDUs. So understanding the trade-offs, going with the larger capacity tap-offs to the cray tap-offs, that would help us understanding what kind of capacity we could cool with liquid solutions.
So is this a useful discussion for you, or do you like where it's going there, Jason?
Yeah, absolutely. And then if we can get in more detail on what the CDU configuration can look like, what they can accept, what temperature ranges and sizes, that would be helpful too.
Very good. So there was a conversation going back and forth, I think, between John Gross and Don this week, really relating to making a chart. And one of the things that is related to this, and I'm actually taking this not from a mechanical engineering anything, but from somebody that does programming about artificial intelligence, which I thought was interesting because it's about heat transfer. And made a nice little graphic about the MC, or the heat balance equation. So this equation, right, is, a lot of people on here can work this equation and come out with something. So one of the other discussions that we've been having is, how do we quantify what we recommend or what we say is available to you based on what's both the water temperature and pressure conditions, but also the size of the pipe. A couple ways to go about doing this are to say, well, okay, right now in our data center, we have this 8-inch header with a bunch of 4-inch drops that were for crays, or they're for future. What can we get out of that for total power if we had 100% effectiveness? Or we can go the other way and say, let's pick some standard nominal sizes. And a lot of debate back and forth on this. Like, so if we pick up a nominal size and say, okay, we're going to go with 250 as the smallest size, right? Is that too big, too small? Does it coincide with a lot of what's nominally available in the market from different manufacturers? And we'll work it backwards and say, here's the size pipe you need. So any guidance on that, any thoughts on that? And because my thought on this real quickly is, if you're building a data center with provision for liquid cooling on day one, your design staff is going to be looking into all these details and working up from that. If you are getting a data center that's existing, then we're probably more where you're looking for help and trying to figure out what's coming off the wall. So those are the two sides of, I think, that equation. At least I'd like to hear anybody's feedback on how we should go about maybe addressing nominal sizes. Should we address nominal sizes? I'll take an example. You might have this might be a liquid cooling solution that does 100 kW. This is a rear door heat exchanger on a rack, which does 35 kW. If I make an assumption that I've got 8 racks at 35 kW, do the math out, I could say, well, there's a pretty good size for an example, right? But if you're this guy, you say, well, 100's actually what we want to base it on, or 200. And then the CDU manufacturers are going to have a different number. So again, I don't have a clear understanding of where the nominal sizing recommendation should come and what we should do with those. At the end of the day, do we produce a chart that says, based on your pipe sizes and your delta T, here's how much kW you could theoretically support? Or do we go the other way? Do we say, here's a chart of 100, 250, 500, 1,000, 2,000, and here's what you need to support it? Because that should be a deliverable from this subcommittee.
Right. So kind of amplifying that a little bit. The concept, we'll probably end up with maybe a small library, 3 or 4 different kinds of reference designs as we go through. For the first one we're looking at, we'd be looking at what is the minimum size reference design that a data center, a decent sized multi-tenant data center would sell cooling at. And I don't know if Jason, you want to, I mean, what's the, where's your pain point?
Well, a couple of thoughts. I mean, a couple standard sizes that would definitely help, but I think really a flow calculation so we could help determine, because you have so many different variables out there. Listing them all out in a table, I think, would just take up way too much space.
So what we're looking at is maybe just choosing a KW number. Is there a, when you sell, what's the smallest amount of KW that you would sell somebody? 250, 400 to actually make it worth your while to provision for liquid distribution?
Yeah, usually they're in the 1 megawatt or above capacity.
Okay.
But you could look at, like, the smallest increment could be a single cabinet. And what's the smallest single cabinet liquid cooled? And you could say air cooled can go up to 20, 25. So maybe you say the smallest liquid cooled cabinet might be 30 kW. How would you solve for a 30 kW application?
But would you solve for one, or would you actually have the tap off your main header for, say, 8 of those, or be the minimum size of consideration? Because what you're seeing here in the drawing, the cost risk factor is how many taps you actually want to put on your main loop.
Yeah, well, I think you just identified another case. So where you have a heterogeneous environment where you have liquid cooled and air cooled, and perhaps you only have 50% of your cabinets requiring liquid cooling. How do you solve for that?
Okay.
We're trying to get a little bit ahead of ourselves in thinking in terms of what sizing to do. I think approaching this from an engineer's standpoint, I don't care so much what the size is. I care more what I'm doing with the numbers of the CDUs. Let's say, I've got a, let's say what John is showing here is a 50 kW tub with another 50 kW of air-cooled rack. So we've got a total of 100 kW. We would ask the question, is that the full capacity that we would get to? So we're at 100 kW, or are we going to grow to 500 kW? So I don't care so much that the CDUs are sized at 100 or 500. I care more, how do I match the CDUs to what my projected total load will be? So I don't have to have a number, this many kW. I have to think in terms of how many CDUs will I be putting in there, and what is my redundancy? Do they all operate at the same time? So the sizing, the pipe size, the piping configuration is kind of less important, and that's on an as needed type of basis. But the kind of questions I think that the engineering community are asking themselves is, if everything downstream of the CDU is purchased from a vendor, the buyer has some flexibility. The vendor is going to give me 100 kW CDU, and I'm saying, no, I don't want 5 CDUs all lined up. Give me something bigger, and I'll work with that. I'll work with maybe 2 side by side, sized at 500. That's kind of a design process, and we need guidelines to really how to figure that out on a larger scheme without getting into the specifics. I think that is generic enough so that we can take the guideline. It is very anonymized in that sense and not prescriptive. This is the bigger picture of how we match CDUs to projected future loads and how we interconnect them.
There was a lot in there, Valley, trying to unwrap it a little bit. So if we don't start with the nominal size of a CDU, then it's hard to make, I think, if I followed your.
Yeah, I'm sorry, I was muted there. I'm wondering if there's some value to start out thinking about how much power do I provision for that area on the floor, right? That I'm going to support some liquid cooling in. And then just like, it may be arbitrarily or a swag, what percentage of that power that I provisioned do I think could end up liquid cooling? So if I've got a cluster of racks out there that I think I'm going to put some amount of liquid cooled racks, maybe some tubs in there, whatever, right? And I got a megawatt there. I say, okay, maybe I'm going to provision for 80% or 800 kilowatts. Really, maybe a crude way to look at it, but maybe a simple way to get the conversation started, right?
Well, John, that's exactly what I was kind of thinking. Is we just pick a number, be it 400, be it 800, pick a nominal number, just to, and then recognizing that in most cases, no one's going to hit that number. If I choose 800, John Rafkin's or Jason Rafkin's going to go with 1 meg. But conceptually wise, so he's going to have to use slightly bigger pipes, slightly bigger CDU, slightly a little more of this. But just for the purpose of getting people to understand, you're not going to go off your main header and tap 100 kW drops off your main header. That's just not for the, at least I don't think people are going to do that. So,
didn't Jason suggest just that at one point?
Jason, is that what you're thinking? A bunch of taps off for 100, or would you, what off your main header? What's the smallest you'd actually do a tap?
Probably about 200 to 300.
Okay.
And then go to a large CDU that can service multiple cabinets, like this row here.
Now, you've also done designs that don't use CDUs, but well, let me rephrase that.
Yeah.
Would you always use a CDU just to isolate the volume at the very least? Okay.
No, we've used chilled water, elevated chilled water, and also condenser water directly to the cabinet, to a rear door heat exchanger.
Right. So a couple different things we're talking about here. So just to kind of give a little bit of background on the conversation that Don and I were having and John Minash were having earlier this week. So the thought behind, excuse me, the connection size discussion was really more for kind of the IT managers, the IT planners. They're trying to figure out, you know, at a high level, is this even feasible for me to put this much load in a certain area? Basically by saying, okay, if you got 250 kW and your system is at a 5C delta T, then you need this size pipe connection in order to be able to handle that. Whether there's a CDU involved, et cetera, that's what you need in order to get there. Likewise, if you've got a 6-inch connection and you have a 9C delta T, then maybe you need you can support X number of kW. So it wasn't really so much to drive the engineering people as it was to just kind of help the IT planners to figure out what's feasible from a cooling perspective. The other piece that I would throw out there is that in existing data centers that are going through a conversion from traditional air-cooled solutions to higher density stuff, a lot of times what's happening is they're going in and they're pulling out CRAWs and they're wanting to connect back into the connections where the CRAWs were sitting before. Whether that be CDU or kind of Don, what you were talking about, do you go and you put in taps for drops for 15 racks off the main? Well, no, you wouldn't come off of where the connections for that crawl were, and then you'd run a new header that has the taps off of that, kind of like what John Minash is showing here, just pretend maybe or maybe not without the CDU in the middle.
Appreciate the summary. I hope people, the challenge, what I see is people at day one are not, to a large extent, doing a large amount of liquid, or they have no idea what their liquid footprint is going to be 4 years from now. And so that's the key aspect of the reference design discussion is what do you want to provision? How do you want to provision to make sure that when 4 years passes and you need to plug in liquids into a older data center, can you do it just by pulling out the CRA and plugging in a CDU? And that may get you part of the way, but if you don't have a path left open for the pipe to go, it's not going to get you any further. So those are areas that we're hoping to try to help with the reference design. I'm going to hand it back to John, and we'll try to figure out how to summarize this. But I think ultimately we're going to try to pick a size and do a reference design around that. I'd probably lean.
Hey, Don.
Go ahead.
This is Greg. Just kind of from the street level as a non-engineer, but with a lot of activity going on in this space right now, I would recommend, kind of 2 tracks, right? You want I think reference designs are a great idea. I've been talking to, data center operators and actual end users, and having the easy button obviously would be important. I think there's 2 paths. There's new build and there's retrofit of legacy site. I think you need to have get container options for outside the building if there's no way they can put it in the building. But I also think maybe you want to start at the rack of the top products, like whether it's NVIDIA or Dell's Liquid, or pick the 3 or 4 people that are actually having success selling these types of solutions in the market. Look at what their reference designs for their racks are. Have a design for the NVIDIA, A100 at 6U at 6.5 watts per deal. In different data centers, some will be able to accommodate a rack with 4 of those in it, which would be 26 kW. Some will be able to, some are looking at going higher with 50. Some of them are going to have a string just like you have, and there's only going to be 1 A100 per rack. But have building blocks that start at what the consumer is actually going to buy and back up into the infrastructure, so you can figure out, we're coming at this from the perspective, we're going to, like we've always done, here's our infrastructure, here's what we're capable of, make it fit. But today, compute's being driven by business lines, accelerated compute and GPUs being driven by business lines, and it's ultimately all about the application and where it needs to be. And with latency and these other things, as phase 2 of this OCP effort, there's probably going to need to be, how are we going to do this at the edge as well? So just some food for thought.
The edge discussion is a very valid one, and actually there was just some advice that came out from ASHRAE TC 9.9 on edge standards. And because of the smaller the data center, the more likely the solution is going to be a proprietary, very custom solution. And I don't want to bite that at the first effort.
Yeah, no, I get it. But like even on this string, you should probably tinker with what are the top 2 server types likely to be found in that string. And it could be NVIDIA, it could be Dell, it could be AMD, Intel's, maybe those are good 4 places to start. They're the larger players in the market, and figure out, all right, what would that string look like with those various technologies in it, and what's required to support that.
So one thing to revisit real quick as we say this is...
Don, can I add something very quickly? I mean, our first document will never be our final and ultimate document.
Right.
It will always be a work in progress.
Mm-hmm.
So, I mean, from my point of view, I think that the most important thing is that we start somewhere and then we build on that.
Yeah.
It will never cover everything, our first document, ever.
So I would also throw in there that we need to keep track of the fact that the purpose of this working group is to focus on the facility side of the system. And at the end of the day, we've got BTUs that we're trying to pull out of an ACF solution and get into the facility cooling solution and reject some way. Whether that's whether those BTUs are coming from an NVIDIA solution or they're coming from a Dell solution or whatnot, I don't really care. I care what the flows, the temperatures, the delta P's are.
But to Greg's point, and one thing I would like to highlight, Greg, is if and I think this is your first call, but there actually is committees in OCP called Advanced Cooling Solutions that are looking at rear door, cold plate, and immersion.
Yep.
And those would be the ones that are focused on answering, I think, a lot of the questions you just raised. The mission of this team is to plug in the advanced cooling solutions into a data center. So we're going to take what they're already doing and working with the NVIDIAs and such, and we're just trying to make sure, as John Gross was pointing out, we're taking it from the facility side to the IT and make sure there is a place to plug it in. Does that kind of balance out the discussion?
Yep, I think it does. It puts the boundaries on it, right? We have to abstract it away a bit from the actual equipment to things that we can deal with at our interface, right? Which are delta T, pressures, supply temperatures. Back to that point, I had mentioned earlier, maybe do we provide a chart that has recommendations based on KW? And somebody made the point, it could be a rather unruly chart, and I agree. But I think we could lock one thing down, or at least into a couple nominal numbers, and it's something that John Gross brought up, which is really a big driver there is going to be delta T, right? So if we picked a few delta T's, we could have I think a manageable chart that gave the user an idea of how much total power they could do for a given pipe size or what have you. Any thoughts on that?
I think it's a great idea. I have, back to my engineering time, I have touched a chart to calculate the pipe size. It's very easy to use. But when we do this, we have to think about the maximum allowed speed of the medium in the pipe to calculate the pressure drop. But this is only a discussion we have to take in account with us in our group here. So if, let's say we go to a speed of 1 meter per second as maximum, so we can calculate the pipes for the examples for the manager to see how big the pipes will be.
So for simplicity, we would probably start with 1 or 2 velocity limitations, if you will. We'd assume a velocity, we would assume a delta T that is reasonable for the industry, and then recognize as part of the equation that if you change your velocity limitation, if you change any part of the Q equals m dot Cp delta T, then your pipe size and the physical size of your structure will change accordingly. Does that make sense?
The pipe size and the CDUs and all the rest of the equipment can manage a lot of different water velocities. Control, that's what control systems are for on pumps and things like that, to speed up and slow down the flow rate. And those piping systems and pieces of equipment can manage a great variety of different flow rates. Now, I get the message that if you go too far, that gee, you're going to need twice the size of the pipe, or maybe 2 pipes to get that much water there. But in general, you can, the mechanical equipment can deal with those variations.
Yeah, but Bruce, would you say, are there standards you'd point to either in the North American market or internationally on the high end of those, right? So like Fitchoff was mentioning earlier, if we had a 100 millimeter pipe, maybe there's a standard we can point to that says, above this velocity, there are problems.
Well, yeah, there are. ASME has guidelines like that, just for the design of piping distribution. The power piping codes have got exactly that, to prevent erosion in the walls of the piping from having it move too quickly because of the turbulence in the elbows of the other fittings. And but you've got to be moving pretty fast to reach that kind of
Yeah, agreed. But what I'm saying is, if we're going to provide some guidance on, we need to take what maybe our max limits are from something, and that's going to be dependent on. Well, it obviously would be dependent on the type of pipe, but let's forget type of pipe for a second. We just say, in North America, we have ASME. What's the standard we might point to outside? Because it's probably different for different size pipes. It's not always a meter per second, right? It depends on the diameter of the pipe.
Well, like X-ray, ASME is a global standard, and other countries pick up their own standards and might change them a little bit. That's always been a global standard, like X-ray is. And
harmonization.
A great place to start.
X-ray is not the global standard. As in Europe, we have own standards and working with this, and use the X-ray standards only for recommendation, but we design our own standards. So X-ray is
that's what I was saying. Everybody has their own standards. Everybody has their own standards, and they're different a little bit, but they're all fundamentally the same, and they've typically come from the American standards from many, many years ago.
So guys, just to kind of, as far as the pipe velocity piece goes, I know this standard is a bad word in the data center industry, but 90.1 actually has guidelines for pipe velocities, and it's all energy driven. But when you go and you look at what those pipe velocities are and you compare that to what is typical best practice for hydronic system design, it pretty well aligns. So if we want to reference a standard, I think that would be a good one to go to, because and that's also given the fact that there's usually very tight alignment between 90.1 and the IECC.
Yeah, agreed, John. That's right.
Perfect. Perfect. Okay. Yeah, no, I agree. The harmonization was what I was looking for, and I think you nailed it, John. That's probably the place where that standard in 91 probably references some others like ASME, right? Okay.
So how about for this? I was going to say for this this particular discussion, how about we show the way to size the heat exchanger and the pipes in terms of the math, like how do you go about sizing it, but then do apply the math for a few cases, right? Yeah, for different capacities, maybe 2 or 3 different capacities, so that someone can see how the math's been applied and run their particular example along similar lines, right?
That's a good idea, but before we go there, I think it's important to help people decide whether or not they need a heat exchanger in the first place. Not everybody needs a CDU. You know,
right.
Heat exchanger, it's not like the same thing as water to the chip. So a user really needs to have a grasp of how he's going to make that decision first.
Yeah, I agree with that, I suppose, yeah. You're saying those big boxes on the right, whether it has a CDU or not is, whether it has a heat exchanger or not is a critical design consideration, right?
And by the way, when I was mentioning, you know, recommendations as far as KW and relating that to pipes, I wasn't necessarily talking about one or the other, right? Either a primary loop or a secondary loop, or a case where the whole loop is the primary loop. For example, you know, if you've got a dry cooler running higher temperatures. I was just in general saying, if we need to give somebody guidance as to how much KW can they pull off of a given size based on a given delta T, that's a helpful number, right? They know they've got 5-inch tap offs on their, say, chilled water. They don't know what that means. You know, they know it's 5 inches. They maybe can figure out the GPM, but they're not going to know what it means for KW. That was the intent that I came up with. So let's close that one out. Does anybody, do we want to proceed with providing some kind of a recommendation as far as a chart or a graphic that shows how much you could sustain as far as max KW for a given pipe size, or is that out of scope and maybe in the weeds details that we don't need to cover here? Thoughts?
I'd like to take a stab at a reference design and possibly run it by some people on this call, just to, so like some of these things, I'm not going to do the pipe calculation. I'd rather have someone else do a pipe calculation, but with a fixed value that we pull from 90.1 and things like that. And just see how it, once we come out with something, let's see if it actually does have value. One of the challenges I have is it seems like our industry always underestimates where we, by the time we finish something, what's really out in the real world is much bigger than what we started with. So initially I was thinking about 250s being a standard reference design size, which is probably fairly much a standard, but I think by the time we finish this percolation and stuff, we'll find that more and more people are selling data center in units of 500 kW or liquid. So if we just arbitrarily try a pilot project right now, say, I don't know if there was an objective, say for 500 kW, came up with some a specified velocity, a specified delta T, and then see how much we can work around that and see if it's a useful model for us for future, for discussions, for sizing, for other things of that nature, not just of the the pipe, but of potentially the footprint of the CDU, the footprint of the heat exchanger, and things of that nature, and then the downstream distribution pipe. And recognizing that all these will be based on a fictitious set of numbers that are reasonable, but not necessarily what we're going to see. And we do recognize that there's a reason that we employ engineers when we do these designs to check these numbers to make sure they actually apply to a specific site. But when we're trying to go to a specific customer, if Jason was trying to sell space in his data center and just conceptually try to explain it to a customer, here's what you're looking at, is there a simple way to do that so that Jason and not just Stack, but all the data center owners could actually say, okay, this is roughly what we're designed to. Any thoughts on what I just said?
I like the idea. It's auch a John Minaj idea is fine to do it, to help the IT guys to understand what technology they have already in the data center and if they can deploy such cooling systems. From the engineering side, we don't, but I think from the IT management side, they need such help to see if the data center can fit liquid cooling devices.
Yes, that's exactly what I was trying to relay for your job. And the reason I'm glad it came across, because I'm not saying we get down and design pipe systems. Designing piping systems and cooling systems is not a hobby, it's a career. And people that we're going to be providing this output for are not doing that, right? So we're just giving them a basic, big idea of what they can do, and then the pitfalls and some guidance on how to do that.
It's as much like what we've been doing for years already, and that is for crack units and cray units. You know, we're pushing water out to the space, and if we want more density into the space, then we need to bring in more units and we need to bring in more piping. And what you'll be showing people is that for this kind of a heat load, you'll need a larger size pipe, and that means that in the original design, as you want to try to future-proof your space, that you'll have fittings and or nipples on your piping that are different sizes to accommodate branch lines that come off of it to run it into heat exchangers or rear door heat exchangers or whatever in the middle of the floor. So it'll be just a pipe size per kW.
Yeah, I think that's pretty simple.
Hi, this is Masood. I want to also add a point here. I think a pipe size and also like pipe materials will be very important, because like you guys mentioned, the ASHRAE 90.1, I think the velocity is for some of the latest technology plastic pipe, the ASHRAE 90.1 has is too low, like 7.5 for larger size pipe. I think the plastic pipe can carry water with a lot more velocity, like 10, maybe 11, 12, something like that. That is probably worth to look at it at that angle, because the new pipes actually carry a higher velocity water, the plastics one, I think.
Well, agree. You've got to specify the pipe, and if you're using different materials, then the pipe size varies with the material: plastic, copper, or steel, whatever you prefer to use.
Agreed. Well, we're at the 5-minute mark for this this call. So I'd like to circle back and say, if we, and I will put more of these together and submit them to the team via email maybe. If we provide some reference designs, do we think that in our paper or as a IFC file, for example, that would be helpful for users? Or do we just want to provide some graphics with arrows and explanations and point out pitfalls and what have you when we provide this document, so to speak?
Hey, John, this is Rich Whitmore with Motivair.
Hey, Rich.
How are you? Sorry, I missed the first call. This is my first time joining. But we can give you some reference guides if you want on CDUs. And I would suggest maybe a band of different ITDs, as was discussed, using different water temperatures to the CDUs.
Yeah, Rich, if you've got something already put together, please share it and we can take a look, because that's the
I would
kind of
also
work we'd want to do.
I know we're at the end here, but I would also just caution the team. I know we've got this divide between the infrastructure piping and then the piping direct to the IT equipment. And there is rapidly evolving, not just technologies, but the thoughts by which this is done. And I think that the group should be careful with material compatibility and things like that with fluids as to what we would specify on the IT side of those piping loops.
Yeah, and one of the topics that came up earlier is, there is a split here. We are dealing with the facility side, and initially people thought, we're just talking this, but if there is no PD CDU, we are talking the piping down thorax. So this is really all in scope for us. Sometimes this secondary loop is going to be prescribed by the equipment manufacturer, and all of the things that you're talking about, Rich. The material compatibility, for example, if it's a refrigerant or a dielectric or something else that that has to be specified by others. So when it's in the open realm of its general piping, we can handle that. But when it gets to something like a proprietary fluid that we don't know interactions or how it reacts, then that has to be under the equipment manufacturer. So with that, I'm going to say thank you to everybody. I don't want this to run over. If you have any comments, please, on both the way we held the meeting today or any of the topics discussed, please email Don or I, and we will get them out and try to address them on the next meeting. So have a good day, and thank you everybody for attending.
Thanks, John.
Thanks, Don.
Thank you.
Thanks.